Okay, so the last section we're going to look at for this week continues what we did yesterday, 4.2 part 2, except yesterday, this is what we did. We looked at graphing problems where the degree in the top was less than or equal to the degree in the bottom. Okay, and we saw the kind of graph we got. I think we had one that looked kind of like this. It was in 3 pieces, and it had the 2 vertical asymptotes, 1 horizontal, kind of like this. And I think we only were able to sketch one of them, but that's pretty much what they all look like.
I think that was on the homework list.
Yeah, there was one on the homework like that too. So that kind of graph is what we can get when there's 2 vertical asymptotes and the degree of the top is smaller than the bottom. Okay? When it's equal, it still can look pretty similar. It's just the horizontal asymptote moves up a little, but it still is in the same 3 basic pieces. What we're going to look at today is what happens when the degree in the top is bigger, okay? Bigger than the bottom. When that happens, the graph can do something a little different. Okay? So kind of problems we would have done yesterday, you would have had something like 3x squared minus 4x plus 2 over x cubed minus 6. That's a problem we would have done yesterday because the degree in the top was smaller than the bottom. Another one we would have done yesterday, something like 4x squared minus 8x plus 6 over x squared minus 3. That's where the degrees are equal. Okay. Now we're going to do it where the number in the top is bigger than the bottom. So any question on what the difference is between what we're going to do today and what we did yesterday? Just going to have a bigger number in the top. Okay, so when the bigger number is in the top, there's something that we're going to have to find called an EBA. Okay, it stands for End Behavior Asymptote. Okay, and the EBA, even though it's a new name, we've never said that before, the way that you find it is something we already do. Okay? It's something we did back in section 3.3. All right, so let's say that you have a problem. Okay? When we actually do one, it'll look something like that. You'll have a polynomial in the top. Okay? You'll have a polynomial in the bottom. I'm just writing them generically because I don't know what they are. Just say h of x is in the top, g of x is in the bottom. Okay, when you divide those 2 things with long division, there's 2 parts to your answer. What do we call the 2 parts? Quotient and remainder. Yep, and the quotient is the EBA. That's all you have to do. So the quotient, we already have been doing quotients. We're just going to not call it the quotient when we write our final answer. We're going to call it the end behavior asymptote. Okay. So when you divide h of x by g of x, the quotient is the EBA. So instead of writing end behavior asymptote, I'm going to abbreviate that EBA. Right, so new word to kind of describe something, but same process we've been using from chapter 3. Now, some EBAs can get pretty complicated to sketch. I might have you find an EBA that is a little more complicated of an EBA, but not have you sketch that EBA. Because finding it just means doing long division. Sketching it can get tricky because sometimes the EBA isn't straight and it starts to curve. So if the EBA starts to curve, I'm not going to have you sketch it, but I would have you just tell me what it is. Okay. so you don't need that. Okay, so any questions on how to find the EVA? It's just the quotient when you do long division, that's all. So let's try a problem. So the directions here say to find the quotient, find the remainder, and find the EVA. It's really just testing to see if you know what EVA is, because if you do, finding the EVA isn't really any more work than just doing the first two things. All right, so let's set this up and do our long division. So we got x minus 2 on the outside. And can anyone tell me what I'm going to put on the inside? Got to be a little bit careful.
2x to the third
Yep, so that's good. 2x to the third.
minus 4x to the second plus 3.
Oh, plus 0x.
Right, plus 0x plus 3. So make sure you fill in every term from the highest exponent to the lowest. If you don't, you're not going to have space to put x's, and then things are going to get messed up. Okay, so now take 2x cubed and divide it by x. What's 2x cubed divided by x?
2x squared.
2x squared. Yep. So we get 2x squared. Multiply the 2x squared back out. What's 2x squared times x?
2x cubed.
2x cubed. What's 2x squared times negative 2?
Negative 4x squared.
Negative 4x squared. And now we've got some columns. And what do we do with the columns?
Subtract.
Subtract. Okay. What's 2x cubed minus 2x cubed? That's gone. What's negative 4x squared minus negative 4x squared?
0.
Yeah, that's also gone. So those both cancel. That usually doesn't happen, but it did here. So now we bring down the next term. Actually, we can bring both down if you want. And now you have 0x divided by x. Well, there the x's cancel, and what are you left with? 0. So you're done. You could put plus 0, but I mean, you don't really need to, because then you'd be distributing 0 back out. 0 times x. And what's 0 times negative 2?
0.
You're just getting all zeros. And then what do we always do with our columns? You're subtracting, but you're subtracting zeros, so those just cancel. And then 3, take away nothing is what?
3.
Just 3. So the remainder is just 3, but we could have stopped because we don't care about the remainder. Well, actually, did they want the remainder? Oh, they did, yeah. Okay. So they did want the remainder.
That's okay, because we still have it.
So, what is my quotient?
2x squared.
2x squared. Don't put plus 0. So 2x squared. What's my remainder? 3. And what's my EVA?
2x squared.
It's the same thing as the quotient. Yep. 2x squared. And if you want to write it as a formula, like you want to graph it on the calculator, we're going to type it in as y equals 2x squared. That's the EVA. It's really y equals 2x
Is that
squared.
like, all, like that's it?
For that problem, that's it. Yep. Okay. Any question on that? All right. So we've talked about two things now that sound kind of similar, but they are a little bit different. We've talked about EBM, that's end behavior model, and EBA. There is a difference how you find them. Okay. The EBM, that's the fast one. All you have to do is take the highest degree term in the top, divide by the highest degree term in the bottom, and you're done. EBA, that's the long one. Okay. So EBA, you need to do long division. Okay. Sometimes the EBM and the EBA could come out the same. Sometimes they could come out different. It depends on the problem. The reason, in this one, the EBM and the EBA would be the same. And the only reason that that happened is because we had something extra canceling out here. If that had not canceled out in this step right here, then the EBA would have been different than the EBM. So I would say most of the time it is more common for them to be different than to be the same. Now, when the degree of the top is less than or equal to the bottom, you will always have asymptotes that are straight lines. And that's what we saw yesterday. The degree of the top was always less than or equal to the bottom. There were two kinds of asymptotes we talked about yesterday, and they were both straight lines. What were the two asymptotes we talked about yesterday? Vertical and horizontal. Those are the only asymptotes we talked about, and those are both straight lines. When the degree in the top is bigger, flip that around, bigger than the bottom, then we can start to get asymptotes that are not straight lines. They can curve. As far as drawing a curved asymptote, it can be a little tricky. So I wouldn't have you draw it, but I might have you find it. So what would a curved asymptote look like? Well, let's say this line in red, or this curve in red, represents an asymptote. If you had a graph where that was an asymptote, it might do something like this. As you draw your graph, it's getting closer and closer and closer to the asymptote, but the asymptote isn't straight. It's a curve that it's getting closer to, not like a straight line that it's getting closer to. That's the difference. So yesterday we got closer and closer to something that was a straight line. Today we're going to get closer and closer to something that's curving. But the important thing is the difference between how you find EBM and EBA. Which one uses long division? The EBA, so that one takes a little longer. The EBM, that's what we did in the homework last night. Any question on that? All right, so now let's verify what we just did in that last problem. In that problem, we think that 2x squared is the EBA. Well, we can check it. Let's type in the original problem. So 2x cubed minus 4x squared plus 3. We're going to divide by x minus 2. And now type the EBA in y2. It's 2x, what was it? 2x squared. So if that's right, then what's going to happen is as we look left and right on the graph, the blue one and the red one should be getting closer and closer together. They're not going to do that near the origin. That's not what the EBA is. Think of the letter E in the EBA, end. The ends are on the left and the right. It's not the middle, it's the ends. So you're going to look far away from the origin. Let's try zoom 6 and start to see what we're looking at. Okay, so here's our graph in blue. And in a minute, you're going to see the EBA in red. Okay, let me make that a little bigger so we can see it. So what's happening there as you continue to head to the left between the blue and the red?
They're getting closer.
They're getting closer. Remember, that red one, that should be dotted. In fact, I can make it dotted so you remember that's the, well, if I make it dotted, it might be harder to see. But the red one is the asymptote. The blue one is the real picture. So the blue one is getting closer and closer to the red one. Now, the red one continues up. Does it look like the blue one is continuing up
Yeah.
from what we can see? No, it looks like the blue one is just going straight down. At some point, the blue one does start continuing back up. If you set your Ymax at like, let's set it at 50. Let's see if we can see a little bit more. So there's the blue one. There you go. So there was a part to the blue one we couldn't see. Now, watch the red one. Now you can see that the blue one and the red one are getting closer and closer together on the ends, not in the middle. Okay, something weird happens in the middle because we have a vertical asymptote. So in the middle, it's almost like the parabola was cut, and then you took the two ends of the parabola and you bent them in opposite directions. That's what's happening with this blue one. Okay, but you're like right under the microphone. It's going to pick all that up. So when you're doing that, you want to make sure you graph it, look at it, and then see if they're getting closer and closer. If they're not, then the EBA that you found is not going to be the correct EBA. Okay? But this I can tell it looks correct because to me they're getting closer and closer together. And it looks like they are right on top of each other, but they're not. It's just because the calculator only has so much resolution on the screen. But they're always just a little bit separated. So any question on how we found that EBA? Okay. So again, EBA is like a picture. If you were to zoom way out, what does the ends of the function look like? It's going to look exactly like that red one if you zoom way out. Does it do some other stuff in the middle? Yes, but that's not what the EBA tells you. The EBA just tells you what does it look like on the ends, not the middle. All right, so let's see if we can, okay, so we verified that, use a graphing calculator. Example 6 was to do what I did right there. I graphed it, and I verified that it is getting closer and closer. So we did that. Let's try another one where we find the EBA. Let's try this one. 2x cubed minus 2x squared. So I'm going to call this example 6. 2x cubed minus 2x squared minus x plus 5. Okay, and I'm going to divide by x minus 2.
Is it 2x squared or just 2x?
Yeah, 2x squared. Thank you. So find the EBA. So in other words, find me a formula that would show me what this graph would look like on the left and the right ends. Not in the middle, just the ends. Okay. So how do you find the EBA?
Divide.
Yep. Do long division. So x minus 2 divided in 2. And am I missing any terms?
No.
Nope. So 2x cubed, 2x squared, minus x plus 5. Okay. What's 2x cubed divided by x? 2x squared. Okay. What do we do with the 2x squared now?
Multiply it.
Yep, distribute it, multiply it back out. What's 2x squared times x?
2x cubed.
2x cubed. And 2x squared times negative 2.
Negative 4x.
Okay. Now, what do you do with your columns?
Subtract.
Subtract them. 2x cubed minus 2x cubed is gone. What's negative 2x squared minus 4x squared?
Negative 6x squared. That would be 2x.
2x squared. Because that's negative 2 plus 4. Bring down your next term. What's 2x squared divided by x? 2x. Multiply it back out. What's 2x times x? And what's 2x times negative 2? Negative 4x. And what do you do with your columns? Subtract them. 2x squared, take away 2x squared is gone. What's negative 1x minus negative 4x?
Negative 3, 3x.
3x. That's negative 1 plus 4. Minus a minus becomes a plus. Now bring down your 5. We don't really care about the 5 though. That's going to be the remainder, part of the remainder. We don't need it. What's 3x divided by 1x? 3. That's your EDA. There's nothing else you would have there because you did the squared, the linear, the constant. There's nothing after the constant. You're done. Okay. So is there any reason why I don't need to distribute? Like, does everyone understand why I'm not going to distribute the 3 back out?
Yep.
I don't need the remainder. Okay. So now let's graph the original problem. Let's graph the EDA, and what should happen on the left and the right ends? They should each be getting what?
Close.
They should be getting closer and closer. So this is a more complicated EDA. I wouldn't have you sketch it, but I might have you find it, just like we did there. Okay, we are going to sketch one, but it's not going to be one that curves. 2x cubed minus 2x squared. Let's put in x squared minus x plus 5, and then divide that by x minus 2. Okay, and the EDA is 2x squared plus 2x plus 3. So remember, this is a parabola shape because the EDA has an exponent of 2. So it's going to be a parabola. If I don't see both parts of the parabola when I graph it, I might have to zoom out. Okay, there's the left part of the parabola. Can I see the right part? Oh, that's what I want to know. No, I have to go higher. You can already tell, well, yeah. So if you can see one part, that's good, but you should be seeing it going back up. So which one of those do I need to set higher? Y max. Let's just try like 50. And let's see. So you'll see the blue one come down. Tries to be a parabola, but then it just is like bent and it goes down. And there's the other part of the parabola continuing up.
So where does that even come from? Is that your,
Yeah.
like, are they connected or no?
No.
Oh.
Nope, they're two separate pieces. If you want to, yeah, if you want to see it a little better, you can, set Y max at like maybe 75, 80. So you have two separate pieces. It's like you took a parabola, you cut it, and you bent part of it way down, and then you took the other part and you bent it up. But you have a parabola shape overall, and that's what the EDA is showing you. Okay, let's just zoom in, see if it looks like they're getting closer and closer. Okay, what do you think?
Yeah.
Yep. So the red one is showing you the overall shape of the ends of it.
So what would happen if it wasn't getting closer?
Then that means we found the wrong EDA.
Oh, okay.
Yeah.
Past that.
Good question.
So if you found the wrong EDA, it might look something like, I'll just make a mistake in the EDA. Let's get rid of the 2. Let's graph it now. And then the blue one will look the same because that's the original. But the red one now is not going to look like it's as close of a match. It's probably going to look way off. Let's see.
Oh.
Did I change it?
Wow.
Yeah, actually, I didn't mess it up that much. Let's say we really make a mistake. Instead of just changing it by 1, we change it by like 5. Now I probably messed it up quite a bit.
Oh, okay.
Yeah, that doesn't look as good to me now.
Oh.
It's just not that bad.
Yeah, now it actually looks like they're getting further apart. When I look over here, the blue and the red one, it looks like the gap between them is growing.
Yeah.
That's not
Okay, I get it.
That's not good. Okay? So they should look like a pretty close match. That top one is the correct one. Okay. So any question on finding the EDA there?
No.
Okay. If the EDA has an exponent 2 or higher, You're not going to have to sketch it. I'm just sketching it so you can see that it's right. If the EBA is lower than a 2, then we are going to sketch it. So let's try one when that happens. Okay, so actually it wants to do 2 things here. Find the vertical asymptote and the EBA. Now, let me just kind of explain something. What's the exponent on the x in the bottom?
1.
It's a 1. What's the exponent on the x in the top?
2.
2. What's the difference between a 1 and a 2?
1.
The difference is a 1. Look back at the one we just did. What's the exponent in the top?
3.
3. What's the exponent in the bottom?
1.
1. What's the difference between a 1 and a 3?
2.
We had a difference of 2. That's why when we found the EBA, there was a 2.
Wow.
This time when we find the EBA,
1.
there's only going to be a 1. The smaller that number is, the easier it is to draw. The further apart these two numbers are, the more complicated it gets. So like if the top number was like a 5 and the bottom number was a 1, that's a difference of 4. That's going to be a really complicated EBA because the exponent is going to have a 4. Okay, the lower the difference, the easier it is to draw. So this one's going to be a little easier because it's only a difference of 1. All right, let's start with the vertical asymptote. What would make the denominator 0?
3.
3. Those are usually pretty quick to find if the bottom is already factored for you. Okay. Now let's do the EBA. That is a little bit more work, and I'm going to do that off to the side. How do we find the EBA?
Divide.
We have to do the long division. But the difference between the top and the bottom is only a 1 this time, not a 2. So it's going to be a faster problem. So we have x squared plus 4x minus 1. Okay. What do you get when you divide x squared by x? You get x. What's x times x? And x times negative 3.
Negative 3x.
Okay. And what are we going to do with our columns? We're going to subtract. That's gone. What's 4x? Minus 3x. 7x. And we really don't even need to bring down the 1 because that's going to be part of the remainder. We just need to do 7x divided by 1x. 7. That's your EBA. Now, what's the exponent on that?
1.
1. When you have an exponent of 1, the EBA doesn't curve. With a 2 or a 3 or higher, it curves. But with a 1, it's not. This is basically like y equals mx plus b, which is going to be what shape?
A line.
It's going to be a line. But if you have a line with a slope of 1, is that a horizontal line, a vertical line, or neither? Neither. It's a slanted line. That's the one I'm going to have you sketch. So this asymptote is going to be what we call a slant. Right? A slant takes the place of the horizontal. You cannot have a horizontal asymptote and a slant asymptote in the same problem. Okay? That won't happen. Okay? And that's important to remember. A slant asymptote takes the place of the horizontal. You cannot have both. Okay, so let's get a piece of graph paper and see if we can sketch that. I'll try it on this paper. Hopefully that's big enough. Okay, sketch both of your asymptotes. I'll do those in red. My vertical is at x equals 3. So that will be a line that we never cross. You cannot cross a vertical asymptote, ever. Can't do it. EBA is y equals 1x plus 7. Okay, what I'm going to do is I'm going to go by, let's see, if I go by plus 7, that's going to put my graph way up there. So you know what I'm going to do? I'm going to get a bigger piece of graph paper because I don't want to go off the graph. Let's try Let's go here and use, how's medium? Small, I think is too small. Yeah, it's kind of small. Yeah, we could use that one. Right. I'm gonna make my own X and Y axis. Just put one there, and I'll do one there. Does that give me more room above? That gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, it gives me some more room. Okay, so let me do both of these at the same time. So vertical line at 3. So 1, 2, 3. So that's right there. Oops. I must have turned on the lines. I'm also going to just trace over my X and Y axis to make those a little bolder so you see them better. Hopefully you can see those better. Okay, so I got my vertical line. Now I need to draw this asymptote. What's the y-intercept? 7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. Looks like it's right there as long as I counted right. Yep. And what's the slope? 1. So that means to go up 1 and then over which way 1?
Right.
To the right. So we're going to go up 1, right 1. And I'm just going to put, I'm not even going to draw it dotted. I'm just going to put in a ton of points like that. And that'll give me my 2 sections. Okay. Now, what we're going to do to sketch it is we're just going to graph some points. Okay, so use your calculator, and we're going to need the table again. So this is where I said we'll be doing some stuff with the table because people wanted to see that. We're going to do that right now. So we got x squared plus 4x minus 1. And then we've got divided by x minus 3. Okay, now what number are you not allowed to plug into the bottom?
3.
3. So don't plug in 3. Okay, if you plug in 3, you're going to get an error. We're going to check numbers close to 3. Okay, I can plug in 3 if you just want to see, but it just says error. What would be a number that's just before 3?
2.999.
2.999. And we are at a really big negative number. So just before 3, we're heading down to what?
Negative infinity.
Yes. So just draw your dot as low as you can. That's just before the 3. Now let's check just after the 3. What would be a number that's just a little bit bigger than 3? 3.001. And I'm up at 20,000. So which way does it look like I'm heading now? Infinity. So just put your dot as high as you can. Now, let's check a few more x values. I would say in this, from that green dot to the left. Let's check 1 and just see where we are. 1, negative 2. So right 1, down 2. Right. Let's do another one. Let's do 0. 0, 1/3. So 0, we're just up a little bit. And let's check, I don't know, I'm going to do negative 2 and then maybe negative 4. I'm just plotting some points. Negative 2, 1. 2, 1. And then I don't know what else I said. Negative 5 is negative a half. 1, 2, 3, 4, 5, negative a half. Okay, so what's going to happen in that green section? It's going to stay very close to that. It's going to come up, start to curve. And what do you think is going to happen between the green one and the red one if I could keep going?
They're going to get closer.
They're going to get closer and closer. Yep. So this section basically looks something like that. Now we just have to figure out this other section, and that's what I didn't want to happen. I don't really have a lot of room. I wanted more height, but I don't have it, so that's fine. Let's check 1, 2, 3. Let's check what happens when x is 4. Okay, I'm way up at 31, so that's off my graph. 6, I'm at 19. 8, I'm at 19. 10, I'm at 19. So I'm pretty much, I'm way off the graph. Well, I can give you a hint what's going to happen. It's going to stay kind of sandwiched in this section right here. It can't leave that. Those asymptotes are, it's kind of like those asymptotes are walls that it can't get out of. So what's going to happen in this section is it's going to stay down, it's going to curve, and it's basically just going to keep going that way. As it keeps heading up, the green and the red dot get closer and closer. So it's really these two parts, they don't connect, and they both curve like that. All right, let me show you on the calculator, and I'll make it so I set my y max at like, I think if I do it at like 40, you'll be able to see it pretty good. Okay, there's the bottom part. We had that one, that it comes in, and then all of a sudden that curves down. And that's the top part, but I didn't set it high enough to see it. But that's what it looks like. Okay, so any question on that one? It's called a slant asymptote. And did I write that down? Let me see. I think I might write it down on the next one. Yeah. So listen, you can write that down for the last problem we just did. The asymptote, I don't know if it was example 7. You could just say the asymptote in the last problem is called a slant asymptote. All right, let's try to find another slant asymptote. Okay, let me see. Let me grab another one from the book. Found one. Let me just see if it's different. X squared minus 3x minus 7. Yep. All right, so let's change this a little bit. Okay, again, before we do it, I don't know how big of a piece of graph paper we're going to need, so I'm going to hope this one works out a little better. Okay, so determine the end behavior asymptote, the vertical asymptote, and make a sketch. Okay. Let's try vertical asymptotes first. Okay, when you write a vertical asymptote, it always starts out with what letter? Yep. Yep, starts out with X. And in this case, it would be x equals what number? Negative 3. Perfect. Well, let's put in your vertical asymptote. Now they want the EBA. How do we find the EBA? Yep, long division. So x plus 3 divided into x squared minus 3x minus 7. What's x squared divided by x? X, multiply it back out. And what do we do with our columns? Yep, we're going to subtract. What's negative 3x?
0.
Minus positive 3x.
Negative 6x.
Negative 6x. And you don't need to bring down the 7, because that would be part of the remainder. What's negative 6x divided by x? Negative 6. There you go. That's your EBA. And because it has an exponent of 1, it's not curved, it's a slant. What's the y-asymptote on that? I mean, yeah, what's the y-intercept? Negative 6. All right, so let's see if we have enough room here. So we're going to go down 6. 1, 2, 3, 4, 5, 6. That's my y-intercept. And what's my slope? 1 over 1 again. Yep. So we're going to go up 1, right 1. And I'll go the other way. And what's going to happen, you know what I can do? Let me just stack another grid on top of that one so I can make it a little bit make my graph paper bigger. Because I'm going to need to go lower than -10. So let me take and add another one to it. Choose. I think this one will be fine. Yep. Make it the same size. That's. I think that'll work okay once I just move it in the right spot. It's pretty close. Okay, so I got that. That just gives me some more, gives me a little bit more space.
Mr. Hager, can you sign a paper for me, please?
I can, but can you just come back in like 10 minutes? Yeah. Because what's going to happen is when you have a slant asymptote, you usually get these asymptotes that make an X shape. One part of your graph is in one part of the X, and the other part is in the top part of the X. Now I have enough graph that I can sketch both parts. Just remember, this is my X-axis up here. I don't know if I can get rid of that other line there. Let me see. Group, ungroup. Yeah, I can. We don't need that. That's not really part of this graph. Do that there. Okay, so good. We got more graph paper. That'll work, I think, now. Okay, so let's plug in some points and see what we got. Okay, can someone remind me what was the numerator in this problem?
X plus 3.
X squared
Oh, I numerator, sorry. Minus 3x minus 7.
minus 3x minus 7. Yep, and what was the denominator?
X plus 3.
X plus 3, okay. And that's it. Okay, so where was our vertical asymptote? -3. So let's plug in a number that's, let's start with a little bit smaller than -3. So to the left of it, like closer to me. -3 point what?
0, 1.
Yeah, -3.01. We are at -1100. So just to the left of -3, we're heading down to what number? Yep. So just put your dot as low as you can. Now let's check something to the right, like further from me. What would be a little bit bigger than -3? -2 point what?
9.
Yeah, -2.99. We are up at almost positive 1100. So when we cross that vertical asymptote, all of a sudden we're heading up to what? Heading up to infinity. Okay, so just put your dot as high as you can. Okay, so now at this point I don't need the original problem, so let's look at just our sketch, and I need to zoom out so I can see it all. There it is. Okay, let's pick a point. Let's pick some more points so we can see what's happening in the right section. What would be a good x value to do? 2? Yep, 2, negative, almost -2. So we got 2, almost -2. That looks good. What would be another one? 4. Okay, 4. We're at -0.5 roughly. 1, 2, 3, 4. I'm at -0.5. So I can kind of see what's happening with the red and the green dots. Let's get another one that's kind of in this section right there. -2. Yep, we could do that one. -2, 3. -2, 1, 2, we're up at 3. And I think maybe 0 would be a good one. 0, -2 roughly. Just a little bit past it. Okay, so I can see what's happening there. It's going to come down. It's going to start to curve through these points. And then it's going to get closer and closer and closer to the green dots. That's the shape in the top part of the X. Okay. What would be a good value to see what's going on in the lower part for X?
-4.
Yeah, let's try -4. I'm at -21. Let's see. So -1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21. Yep. Okay, so I got that one. What would be another good x value?
-2.
Negative 2 is on the other side. That's the top part.
-6.
Okay, we could do -6. All right, that's not as bad. -6, negative, a little after -15. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, about right there. And we could do one more. Let's do -10. I think that'll be on my, I can't do -70. I can do -10. Yeah, that's on there. -10, -17 and a half. So -10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and a half. Okay, so now draw that red section. Basically, it's going to kind of come up, start to curve, and then it's going to get down, and it's going to get closer and closer to those green dots. That's a really good picture. Okay, that last one we did, it was a little hard for me because I didn't have enough graph paper to do it. Any question on that one? And is everyone okay if I don't graph it on the calculator? It would look just like that. Okay. So again, what do we call this one? That's like the y equals mx plus b asymptote? That's called a slant asymptote. Yep. And it's the only one that I would have you sketch from this section. You do not have to sketch an asymptote that comes out with like an exponent of 2. Okay, I don't have to do that. Okay, let's look at the last one. So it says use a graphing calculator to graph that. Okay, you just want us to graph it and see what it looks like. So what I'd be looking for here is the window. Just tell me what window you used. What am I going to need when I type that in? I got to make sure I put it. Yeah, put it in parentheses. 2x to the 4th plus 7x cubed plus 7x squared plus 2x, and we're going to divide by x cubed minus x plus 50. Okay, and let's do zoom 6. Now, what's the difference between the highest exponent and the top and the bottom? Difference of 1, which means what kind of asymptote when you have a difference of 1?
Slant.
Yeah, there is going to be a slant asymptote. We're not finding it, but I can kind of see it. It would be in, I can kind of see there would be a slant there. Let's just set the y max a little bit lower. Let's y min, I'm sorry. Let's do -25. Now I can definitely see that there's some kind of line that that's getting closer to, and then it's probably going to continue up that way as well. Okay, so there's our sketch. Is there anything in that sketch that looks like it might be misleading and we would have to zoom in to see it better?
The fact that it's like on the zoom.
Yeah, it's flat.
It's very flat, right? It looks very flat. So I would say for that, that's a good window. Okay? You can't see the flat part, but for that particular part of the problem, that window is okay. Let's zoom in on that flat part. Look at where I just put my box. What did I set my y min and max to if I go by that box? -1 and 1. Yep. So I set it from -1 to +1. And how about my x's? -1, 2. Well, 1, 2, 3. We could do -4 if you wanted. And what about my y max? X max. I would go to 2. 3 I can see it's a little bit further. Let's just go to 2. So we're really just zooming in on that red box. Okay, so when we zoom in on that red box, we get that picture. What are you starting to notice now?
drops below 0 and then goes back up?
Looks like it goes below 0. I really can't even see it that well. So now, let's zoom in just on that again. Instead of -1 to 1, let's do like -0.1 to 0.1. That's extremely small. It's a very, very small window. But watch what happens when you keep zooming in on that red box. What originally looked very flat, now we can see wasn't flat at all. Those are not very big, like, ups and downs. They're extremely small. But the more you zoom in, it's like you're looking at it with a microscope now. The ups and downs look a lot bigger. Okay? So the point here is, if they give you a problem and they ask you to look for hidden behavior, that would be considered hidden behavior.
And would you have to draw that out or tell them?
You just have to say, to see it, I used a window, and tell me what you zoomed into. Yeah. Okay, so I just want you to see that some graphs might look a certain way, but you zoom in, and they're not. Okay, so the homework
Wait, homework?
Or we got homework in
is on page 235, just so you can see. And what I'll do is I'm going to put the test topics in the video, but I'm going to have to do that after you guys leave. But the test will just cover what we did this week, 4.1 and 4.2. Reminder, I'll be after school today if anybody needs to see me for extra help.